Hello and welcome to the third video in the series of real analysis. This is AK Pathak presenting you this video in which we are going to talk about partition, ordering and their use in understanding the concept of rational numbers. Some parts of the video also aim to elaborate upon some advanced concepts highlighting the use of partition, like proving the famous Lagrange's theorem of algebra. So I guess this video will not only be useful for beginners but also be interesting for advanced learners. If you like the video, you may please subscribe to the channel and express your liking by clicking the like button so that more and more people get benefited. Let us proceed to have the concept. Firstly, we talk about partition. The concept of partition is very common to us. It is basically creating disjoint segments of a given region in a meaningful way. For example, suppose we have a room shared by 4 students. Call them as S1, S2, S3 and S4. Suppose 2 students are of the same class. Call them S1 and S4, and the remaining 2 are in different classes. So let us put some different colors for them. Now, during examination, they decide that they need some separation, but for facilitating group studies, they also decide that students of the same class should live together. Then what would be the easiest way to fulfill their desire? The room will be partitioned into segments like this. This is the room. We can create segments like this so that students S1 and S4 are placed in one segment, S2 in one segment, and S3 in the rest of the segments. Now, this is creating a partition. In fact, how could we achieve it? Firstly, we accepted a rule that students of the same class will live together. So, we have a rule that students of the same class will live together, and this is the rule which we put here. This rule facilitated to create a partition of the room. The same idea is applicable in a set. Partitioning a set simply leads to putting the elements of the same nature together according to some rule. Of course, the rule has to be decided by us, which put the objects of the same nature together. We will learn how to formulate such rules, but let us formally define a partition for which we note some of the properties in this example. Now, what are the properties which we observe here? We call this set as X and these sets as X1, X2 and X3. These X1, X2, X3 are called partition sets. Now, what are our observations? Let us write our observations. Now, first observation is the full set X is non-empty. The second observation is that x1 is a subset of x, x2 is a subset of x, x3 is a subset of x. Also, x1 is not equal to phi, x2 is not equal to phi, x3 is not equal to phi. The third observation which we have is x1 intersection x2. This is also equal to x1 intersection x3, and this is again equal to x2 intersection x3, and all are equal to phi. And the last one is that x1 union x2 union x3 is also equal to x. So these are the observations which we can have from this picture. Now, the meanings of these observations are very simple. This first observation is that the full set is non-empty. The second observation is, combining these two, of course, that partition sets are non-empty subsets of the full set. The third observation is partition sets are pairwise disjoint. And the last observation is union of partition sets is the full set. So these are the observations of the example which we had just in our discussion. Now, the another corollary which we can derive from these observations is very simple. Now, in fact, from these two, we can derive a corollary that number of elements in X is equal to number of elements in X1 plus number of elements in X2 plus number of elements in X3. And as we know that in set theory, the number of elements in a set is called the cardinal number of that set, and therefore we can very easily write that cardinal number of X is equal to cardinal number of X1 plus cardinal number of X2 plus cardinal number of X3. Now, if in a situation, not in this example, but if in any other situation, we find that the cardinal number of all the partition sets are equal, say is equal to X alpha. So if I say that X alpha is the cardinal number of all partition sets, then we can say that cardinal X is equal to number of partition sets into X alpha. Now this is the concept which we use later on in proving the Lagrange's theorem. So this is all about the concept of partition with a very simple example. But before we proceed to have a formal definition of partition, let us have two more concepts. In many of the situations, we have a family containing many sets. I mean, maybe having 50 sets or maybe having in a countable number of sets like that. So how to represent that family? The way to represent that family is an indexed family of sets. We create an indexed family of sets, and for that what we take is we take an index set I, and we create a family xi and let the I run over the members of the index set I. It means that for every member of this index set, we have a set in the family. For example, let I is 1, 2, 3. Then the family X becomes X1, X2, X3. And if we take index set as the set of natural numbers, then our family becomes x1, x2, xn, and like that. Let us not confuse that x is equal to xi. This is not the case. So this is not the union. In fact, it is a collection of some sets where in the collection every set corresponds to an element present in the index set. So this type of family is known as an indexed family of sets. Now, if we have a family of sets like this, then if we take any two different elements xi and xj, I not equal to j. So we have a different a pair of different sets, and then the intersection of these two sets is phi. So any pair of different sets, if the intersection is phi, then we call the family to have pairwise disjoint sets. Now let us move to formally define the partition. Now this is the definition which you generally see in books. A partition of a non-empty set X is a pairwise disjoint collection Xi, I runs over the elements of the index set I, of non-empty subsets of X such that X is equal to union Xi. Xi's are called partition sets. But here we are going to frame definition according to our observations. So our observations are like this. Our observations which we had during our example are like this. First is the full set is non-empty. The second is, now I am using the index set, so I can write that xi are subset of x and xi are non-empty where I runs over an index set. The third, I can say that xi intersection xj is equal to phi for I not equal to j, and the fourth one is union of xi where I runs over the index set I is equal to x. Now On the basis of these observations, we are going to have the definition of partition. So, what is the definition we are going to frame? Let X be a non-empty set and Xi runs over an index set I are non-empty subsets of X such that first Xi intersection Xj is equal to phi I not equal to j, and the second is union of Xi I runs over the index set is equal to X. Then the collection Xi is called a partition of X. So we can put in a simpler way the definition of a partition. So now we know that what is a partition, and we also know the definition of partition. Now let us move and grab the concept of the rule which we use in creating a partition. So we can easily observe that one partition set contains elements of the same type. Here we have the rule that pencils of same length should be placed in same segment of partition. On the screen you can see you have some pencils, and we have imposed the rule which you see on your screen that pencils of same length should be placed in same segment of partition. Now you can very easily observe that in one partition set we have kept pencils of same length. So they have some sort of equivalence in the context of our rule that pencils of same length are in the same partition set. Now, rule which associates elements of a set is called a relation. So I write that rule which a rule I can write which associates elements of a set to elements of the same set or to elements of another set is called relation. So this is simply a rule which associates one element to another element. Here we have one set, and therefore the rule which we have imposed here that pencils of same length should be placed in the same segment of the partition is a relation. So we call that pencil P1 is related to P2 if P1 and P2 have same length. So in this way we have related two pencils, and this is a relation. Now you can also observe that because in this case of partition, it is also established that there is some sort of equivalence among the objects lying in the same partition set. And therefore, this type of relation, which is imposing some sort of equivalence between the elements or among the elements present in the same partition set, is called an equivalence relation. And therefore, what is the duty of equivalence relation? The duty of equivalence relation is to put the elements of the same type, same nature, according to the relation which we have defined together in one partition set, you can say. So this is the nature of equivalence relation. So let us formally define equivalence relation. Now this is the definition of equivalence relation. A relation which has three properties. First is reflexive, the second is symmetric, and the third is transitive, is called an equivalence relation. Now what is the meaning of being reflexive, symmetric, and transitive? Let us understand. Reflexive means every element is related to itself. Every element is related to itself. This is the meaning of being reflexive. The meaning of being symmetric is if one element is related to other, then the other element is also related to the first element. So if x is related to y, then y is related to x. And what is the meaning of transitive? If x is related to y and y is related to z, then x is related to z. So these are the types of a relation. Now let us understand with some examples. Suppose we are having family of lines. So let x, I take family of straight lines, if I take, and let R be like this, A R B, or better if I take A R L1 is a line related to another line L2 if L1 is parallel to L2. Now this is the relation which we take. Therefore now you can see that L1 is always parallel to L1. The second thing we see that L1 is parallel to L2. This very clearly implies that L2 is parallel to L1. And the third thing is L1 is parallel to L2 and L2 is parallel to some other line L3. This clearly implies that L1 is parallel to L3. And therefore this relation that L1 is related to L2 if L1 is parallel to L2 means being parallel. The relation of being parallel is an equivalence relation. And therefore what we can say that being parallel is an equivalence relation. But let us consider another example. Now here on the same family, I define another relation and take L1 is related to L2 if L1 is perpendicular to L2. Now I take R in this form now. Now what happens? Can you say that L1 is perpendicular to L1? No, this is not true. The second is L1 perpendicular to L2 implies L2 perpendicular L1. Yes, it is true. Now third is L1 perpendicular to L2 and L2 perpendicular L3. This does not imply that L1 is perpendicular to L3. And therefore, the relation of perpendicularism is not an equivalence relation. So this is not an equivalence relation because the relation is reflexive. Sorry, relation is not reflexive. It is symmetric but not transitive. And therefore, it is not an equivalence relation. So, this type of equivalence relation can be studied further with another practical example. Let us suppose that in a college there are three types of students: the students of first year, then we have some students of second year, and then we have some students of third year, and like that. Now we again impose a rule that students are related if they study in the same class. Now with the help of, this is very simple that it is an equivalence relation as we have already seen in the first example, but just to refresh, I can mention that first, of course, a student A is related to A because A and A read in the same class. If A is related to B, means A and B study in the same class. This means that B and A also study in the same class. If A and D study in the same class, B and C study in the same class, then it simply means that A and C study in the same class, and therefore it is an equivalence relation. Now let us see that how does this equivalence relation create a partition. Now suppose we have to form some queue for distribution of some breakfast or like that. Now what will we do? We will call one student from the assembly of students, and suppose we call first student and the student is of the third year. Then we call another student and suppose it is a student of second year, and then we call one student and suppose it is a student of first year. And now we ask all to follow them according to their classes, and therefore we get a queue like this. So all the students of third year will stand in queue like this. All the students of second year will stand in queue like this, and all the students of first year will stand in queue like this. And therefore we have created partition of this set. This is our set, full set X, and this is the partition which we have created. Now you can see that you have one partition set like this, one partition set like this, and another partition set like this. So these are the partitions. Now this partition, this full partition set contains many students. Now this partition set can be represented by this one student. Similarly, this partition set can be represented like this, and this partition set can be represented like this. So one student can represent the whole set in the partition set. Now you can very easily see that in this set all the elements of the same partition set are present. Now these type of sets are called equivalence classes. And therefore this is one equivalence class, this is another equivalence class, and this is the third equivalence class. So the partition sets which we create due to an equivalence relation are in fact called equivalence classes, and one equivalence class contains all those elements which are having the same nature according to the relation which we have defined. Now let us move further and have some more mathematical ideas. Now let us take this example that A is related to B if A is congruent to B mod n. Now what is the meaning of A is congruent to B mod n? As we know, I am just going to explain a bit. A is congruent to B mod n. This simply means that A minus B is exactly divisible by n. Now let A is equal to nk1 plus r1, where by division algorithm, where 0 is less than equal to r1 less than n. B is nk2 plus r2, 0 is less than equal to r2 less than n. Then A minus B is n k1 minus k2 plus r1 minus r2. So if we say that if A minus B is exactly divisible by n, then r1 minus r2 has to be equal to 0, and this simply means that r1 is equal to r2, and it means that when A and B are divided by n, they yield the same remainder. And so I can say that A is congruent to B mod n. This simply means that A and B yield same remainder when divided by n. And therefore, combining these two, we can say that A R B, this means that A and B yield same remainder when divided by n. Now let us check whether this relation is going to be an equivalence relation. Now the first is reflexivity. A or A is obvious because A and A yield the same remainder when divided by n. The second is A or B implies B or A, and which is called symmetry. This is also obvious because if A and B yield the same remainder when divided by n, then B and A also yield the same remainder. And the third is A or B and B or C implies A or C. This is transitivity. And therefore, if A and B yield the same remainder, B and C yield the same remainder when divided by n, then obviously A and C yield the same remainder when divided by n. And therefore, this relation is an equivalence relation. And therefore, this relation is an equivalence relation. Now, using this relation, we are going to create partition of the set of integers, and with again we are going to make it simpler. Now we see that how this equivalence relation creates a partition, and for this we are making it a bit simpler, and we write that A is congruent to B mod 2. It means I am saying that A or B if and only if A is congruent to B mod 2. Now, what are the possible remainders when you divide any integer by 2? So, possible remainders after division by 2 are 0 and 1. And therefore, the whole set Z can be partitioned into two equivalence classes, 0 and 1. Isn't it surprising? The whole of the set of integers is now put into just two boxes. One is being represented by 0 and the other is being represented by 1. Of course, what is our 0? Now this 0 is equal to 2. This is also 4. So any of the member present in that set can represent that group. Similarly, 1 is also equal to, and like this. Because what is 0? What is 0? This equivalence class 0 is all the elements present in Z such that A are 0. And it means that all the elements present in set Z such that A is divisible by 2. And this simply means that these are the elements 0 plus minus 2 plus minus 4 plus minus 6 and so on. So this is the equivalence class 0. And similarly, we can have this equivalence class 1 plus minus 3 plus minus 5 plus minus 7 and so on. So this is the equivalence class which we have using this equivalence relation. To be more general, we can say that equivalence relation A or B, when A is congruent to B mod n, partitions the set of integers z as z barabar 0, 1 to n minus 1 in equivalence classes. Now we move to know the famous rational numbers with the help of partition and equivalence relation. So let us recall our school days and recall the definition of fractions or knowing the fractions. So what are the fractions? So fractions are symbols of the type A upon B, where I can say that AB are integers and B is not equal to 0. Now, if I take a fraction 1 upon 2, another fraction 2 upon 4, and another fraction 3 upon 6, are they the same? No. As a fraction, they are not same, because let us see what is 1 by 2 means when we represent it as a fraction. We have one braid and we have divided it in two parts. Now here we have two braids and we have divided these two braids in four parts. And here we have three braids and we have divided them into six parts. So you can see that as fractions they are different, but eventually what we note that the one part in each of the fraction is same. What I mean to say that one part is same, so magnitude is same. So what we observe that magnitude is same, and there comes the concept of numbers. So what a number does represent? It represents magnitude, and therefore we have the concept of numbers in place if we are thinking the fractions as one having one magnitude. Now here we impose a rule on fractions, of course on the set of fractions, and that rule is a fraction a by b is related to another fraction c upon d. Of course b and d are not equal to 0 if and only if AD is equal to BC. We impose this rule. Now we will check whether it is going to be an equivalence relation or not. Now first is reflexivity. So A by B is related to A by B because AB is equal to BA, and therefore we have reflexivity. The second is A by B is related to C by D. This implies that AD is equal to BC, and this implies that CB is equal to DA, and this implies that C by D is related to A by B, and therefore we have symmetry. And the third, A by B is related to C by D, and C by D related to E by F. This implies that AD is equal to BC and CF is equal to ED, and this implies that AD into CF is equal to BC into ED, and this implies that AF is equal to BE, and this implies that A by B is related to E by F, and therefore we have shown that the relation is also transitive, and therefore this relation is an equivalence relation. So it is an equivalence relation. Now, because it is an equivalence relation, it will create partitions. It will create partitions. So if we create partitions, then what is the situation? Now, if I take an equivalence class A upon B, then what is A upon B is all the fractions type C upon D such that A upon B is related to C upon D, and this is C upon D such that AD is equal to BC, and therefore in particular if I take half, then we can see that fractions of the type 1 upon 2, 2 upon 4, 3 upon 6, and in general A upon 2A, where A is in Z not equal to 0, they all are in this class. So this equivalence class, this has to be noted that this equivalence class is half, which is a rational number. So when I call half as a rational number, it represents all the fractions present in this set. So half as a rational number is an equivalence class created on the set of fractions. So this is the concept of rational number. So as a rational number, 1 by 2, 2 by 4, 3 by 6 all are equivalent because they are in the same equivalence class. So this is the concept of rational number. Now let us move further and look into the matter in a reverse way. We have seen that equivalence relation creates a partition. Now what we are going to prove now, that every partition induces a relation, and that relation is eventually an equivalence relation. This is very simple. Let xi be a partition of x. We define A R B if A B belongs to Xi for the same I. Now let A B C belong to Xi0 for some fixed I0 belonging to index set. Then what we can very easily observe is first A are A because A and A always belong to the same set. The second is A R B implies A B belongs to Xi0, and this implies that B A belongs to Xi0, and this implies that B are A, and therefore we have symmetry. And similarly we can have that A R B and B R C implies A R C, because if A and B are members of Xi0, B and C are members of Xi0, then A and C are also members of Xi0. And therefore, given any partition, we can have a relation of this type, and that relation eventually will become an equivalence relation. Therefore, we get a very famous theorem known as fundamental theorem of equivalence relation. It simply says that every equivalence relation induces a partition and every partition induces an equivalence relation. This is the fundamental theorem of equivalence relation. Now, in the last, we move to have the proof of a very famous theorem in algebra, and that is Lagrange's theorem, and that also with the help of partition and equivalence relation. Now the equivalence relation which we are going to have in this example is this: A is congruent to B mod H if AB inverse belongs to H. Here we have taken G as a group and H as a subgroup of G. I am emphasizing that this example is for those learners who have knowledge of group theory, otherwise you can escape it. So this is the family of right cosets, and what we are going to show that these right cosets are nothing but the equivalence classes. So let A be in G, and then what is our equivalence class A? Here the equivalence class is all the elements X in G such that A is congruent to X modulus of H. We prove that this equivalence class A is nothing but the right coset H. Now for the element H in H, HA belongs to this right coset HA. Now we have to show that this HA is in the equivalence class, and therefore we consider this AHA inverse, and this is A inverse H inverse. This is A inverse H inverse, and this is equal to E into H inverse, where E is the identity element, and this is equal to H inverse, which belongs to the set H. And so what we conclude, that this element HA belongs to the equivalence class A, and this implies that the right coset HA is a subset of the equivalence class A. Conversely, let X belongs to the equivalence class. Then, according to our relation, AX inverse belongs to H. And so, AX inverse belongs to H because H is a subgroup. This implies that X A inverse belongs to H, and this implies that X A inverse is equal to H for some H in H, and this certainly implies that X belongs to HA. And therefore we have taken X in the equivalence class and we have proved that it belongs to HA, and therefore A becomes subset of HA. Combining these two, we get that this equivalence class is nothing but the right coset HA. And therefore we also know that distinct right cosets have same number of elements. Therefore, we can say that the order of the subgroup H, because H is again in itself a right coset, is equal to cardinal number of the right cosets HA for all A in G. And therefore, it means that order of G is nothing but number of distinct right cosets multiplied by cardinal number of HA, and which is called index of H in G multiplied by order of H, because the cardinal number of a set and the order of a group have the same concepts. It means that the number of elements they possess, and therefore we can see that order of G is a multiple of order of H, and so order of H divides order of G, which is Lagrange's theorem, famous Lagrange's theorem. If G is a finite group and H is a group subgroup of G, then order of H is a divisor of order of G. With this, now we are closing this video and we will meet in our next video. Till then, thank you very much.